Welcome to this coding tutorial. Today, we'll explore LeetCode problem number 405, convert a number to hexadecimal. This problem challenges us to convert an integer to its hexadecimal representation, a fundamental concept in computer science. Stay tuned as we break it down step by step and look at different approaches to solve it efficiently. In this problem, you are tasked with converting an integer into its hexadecimal, or base 16, representation. Hexadecimal uses the digits 0 through 9 and the letters A through F to represent values from 0 to 15. If the given number is negative, the conversion should use the 2's complement method. Additionally, any leading zeros in the output should be omitted. For example, if the input number is 0, the output must simply be 0. The function will take a single integer as input and return its hexadecimal equivalent as a string. Let's explore an example. If the input number is 26, we convert it to hexadecimal by repeatedly dividing by 16 and recording the remainders. First, dividing 26 by 16 gives a quotient of 1 and a remainder of 10. In hexadecimal notation, the remainder 10 is represented by the letter A. Since the quotient 1 is less than 16, it becomes the most significant digit. Therefore, the hexadecimal representation of 26 is 1A. Now, if the input is -1, we use the 2's complement method. On a 32-bit system, -1 in binary is represented as all ones, which when grouped into 4-bit chunks corresponds to the hexadecimal string FFFFFFFF. Here's another example. If the input number is 0, its hexadecimal representation is simply 0. This is because the number 0 remains the same in any base, and there are no leading zeros or other digits in the result. This straightforward case establishes the baseline for handling 0 as an input. Now, let's discuss the constraints and edge cases for this problem. The input number will be within the range of -2 to the power of 31 to 2 to the power of 31, covering both the smallest and largest possible 32-bit integers. The solution must handle positive and negative numbers efficiently while ensuring no leading zeros in the output. Hexadecimal letters should always be in lowercase. Edge cases include handling special inputs like 0, which outputs 0, and -1, which must use 2's complement representation. You must also correctly process large integers, like 2 to the power of 31, and ensure no redundant zeros for powers of 16, such as 16 or 32. Finally, small integers between 1 and 15 should produce a single hexadecimal digit as output, verifying that the function works accurately for all scenarios. To solve the problem of converting a number to hexadecimal, we can explore a few different approaches. The first one is a brute force method based on manual base conversion. The idea here is straightforward: repeatedly divide the number by 16 to obtain the remainders, which represent the hexadecimal digits. These remainders are then mapped to their corresponding hex characters, such as 0 through 9 and A through F. For positive numbers, you continue dividing until the number becomes 0, collecting remainders in reverse order. For negative numbers, you simulate their unsigned 32-bit representation by adding 2 to the power of 32 to the number, which effectively converts it to 2's complement form. While this approach is simple and intuitive, it has some drawbacks, like the need to manually reverse the list of remainders and handle negative numbers explicitly. It has a time complexity of O log number, because each division reduces the number by a factor of 16, and a similar space complexity. However, the overhead from reversing the list and manual handling of 2's complement can make it less efficient compared to other methods. Another option we can consider is an optimized approach based on bitwise manipulation, which leverages the natural relationship between hexadecimal and binary systems. Hexadecimal is inherently a base 16 system, where each digit corresponds directly to 4 bits. Using this connection, we can implement a more efficient solution with bitwise operations. The key idea is to extract 4 bits at a time from the binary representation of the number. To handle negative numbers, we first convert them to their unsigned 32-bit representation by adding 2 to the power of 32, which ensures that we're working with a consistent bit-level representation. Then, in a loop, we repeatedly isolate the last 4 bits using the bitwise AND operation with 0xf, map those 4 bits to the corresponding hexadecimal digit, and append it to our result. The number is then right-shifted by 4 bits to process the next group of 4 bits. The loop continues until the number reduces to 0, with a special case for the input 0 itself. This approach is highly efficient, with a constant time complexity of 1 for 32-bit integers because there are at most 8 hex digits. It also has a space complexity of 1, since the result is built directly without requiring additional structures. While this method avoids the need to reverse lists, it might seem less intuitive to beginners due to the use of bitwise operations. Lastly, there is the library function approach, where we simply use built-in functions like Python's hex to perform the conversion. This is the easiest to implement but doesn't provide much insight into the mechanics of hexadecimal conversion. We have chosen the bitwise manipulation approach as the most effective strategy for solving this problem. This method aligns well with the structure of hexadecimal, as each digit naturally corresponds to 4 bits in binary. This tight relationship makes bitwise operations a logical and efficient choice. Additionally, negative numbers can be seamlessly handled by converting them into their unsigned 32-bit representation, ensuring consistency and correctness. This approach is particularly appealing because of its efficiency, operating in constant time for 32-bit integers. It also avoids the need to reverse lists, which simplifies the implementation and reduces overhead. While it is slightly more complex due to the use of bitwise operations, it offers significant performance advantages and provides a deeper understanding of how hexadecimal conversion works at the bit level. Moreover, it doesn't rely on language-specific features like hex, making it a versatile and portable solution. In summary, bitwise manipulation strikes the best balance between efficiency, clarity, and direct handling of edge cases like 2's complement representation for negative numbers, making it the optimal choice for this problem. In this problem, we are tasked with converting a given integer into its hexadecimal representation. Hexadecimal, being a base 16 system, uses digits 0 through 9 and letters A through F to represent values from 0 to 15. One important aspect of this problem is that the solution must handle both positive and negative integers. This includes edge cases like 0, which directly maps to 0, and the smallest 32-bit integer, which requires special handling due to its signed representation. To solve this problem efficiently, we use an approach based on bit manipulation. The intuition here is that hexadecimal digits correspond to groups of 4 bits. By isolating 4 bits at a time, we can construct the hexadecimal representation incrementally, which avoids more computationally expensive operations like division or recursion. The first step in our algorithm is to handle the edge case where the input number is 0. If the number is 0, we immediately return the string 0, as that is its hexadecimal equivalent. Next, we prepare for the conversion process. We start by defining a string called hex_map that contains all the hexadecimal characters in order, from 0 to F. This allows us to easily map numeric values between 0 and 15 to their corresponding hexadecimal characters. If the input number is negative, we need to convert it into its 32-bit unsigned equivalent. This is done by adding 2 to the power of 32, or 429, 496, 7296, to the input number. This step ensures that the algorithm can handle signed integers correctly. Once the number is in the correct range, we initialize an empty string called result to store the hexadecimal representation. We then use a loop to extract each hexadecimal digit. By performing a bitwise AND operation between the number and 15, we isolate the last 4 bits, which gives the value of the current hexadecimal digit. Using the hex_map, we map this value to its corresponding character and prepend it to the result string. After processing the current digit, we right-shift the number by 4 bits, effectively dividing it by 16, to move on to the next group of 4 bits. This process continues until the number becomes 0. There are several key insights that make this algorithm both efficient and easy to understand. First, the bitwise AND operation with 15 is crucial because it isolates the last 4 bits of the number, which map directly to a single hexadecimal digit. The right-shift operation divides the number by 16, effectively discarding the least significant digit and preparing the number for the next iteration. Handling negative numbers is another important aspect. Since Python integers are signed by default, converting a negative number to its 32-bit unsigned equivalent ensures that the algorithm adheres to the problem's constraints. Additionally, we build the result string by prepending characters because we process the digits from the least significant to the most significant. This approach ensures that the final representation is in the correct order. In terms of data structures, we use a string hex_map to map numeric values to hexadecimal characters, which simplifies the logic and avoids repetitive conditional checks. The result string is used to store the hexadecimal output, and its immutability and ease of concatenation make it a natural choice for this task. Now, let's analyze the complexity of this algorithm. The time complexity is O log number, where number is the absolute value of the input number. This is because we process 4 bits in each iteration, and the total number of iterations corresponds to the number of hexadecimal digits, which is proportional to the base 16 logarithm of number. The space complexity is O1 for the hex_map and other variables, excluding the output string. The output string itself has a space requirement that depends on the number of hexadecimal digits, but this is not included in the algorithm's auxiliary space usage. It's also essential to consider edge cases. For instance, if the input is 0, the algorithm should immediately return 0. For negative numbers, converting them to their unsigned 32-bit equivalents ensures that they are handled correctly. The smallest 32-bit integer, which is -2 to the power of 31, is a noteworthy edge case, as it requires wrapping into the unsigned integer space. Finally, the algorithm should also handle large positive numbers, such as 2 to the power of 31-1, without any issues. Let's walk through a couple of examples to see how the algorithm works in practice. For the input number equals 26, the initial number is 26. First, we extract the last 4 bits using the operation 26 and 15, which equals 10. Using the hex_map, we map 10 to the character A. Next, we right-shift the number by 4 bits, resulting in 26 4 equals 1. We extract the last 4 bits again with 1 and 15, which equals 1, and map it to the character 1. After another right shift, the number becomes 0, so the loop exits. By prepending 1 and A, the final result is 1A. Now, for the input number equals -1, we first convert it to its 32-bit unsigned equivalent by adding 2 to the power of 32, resulting in 429, 496, 7295. Using the same process, we repeatedly extract the last 4 bits, which always equal 15, and map them to the character F. This process continues until all 8 hexadecimal digits are extracted, resulting in FFFFFFFF. These examples demonstrate how the algorithm efficiently handles both positive and negative numbers, producing correct hexadecimal representations. This Python implementation solves LeetCode problem number 405, convert a number to hexadecimal. The problem requires converting an integer to its hexadecimal representation, even for negative numbers and edge cases like 0. First, the function begins by checking if the number is 0. If so, it directly returns the string 0 since the hexadecimal representation of 0 is simply 0. The function also handles the case of negative numbers. In Python, integers are signed, but the problem specifies working with 32-bit signed integers. To handle a negative input, the code adds 2 to the power of 32, or 429, 496, 7296, to the number. This effectively converts the negative number into its unsigned 32-bit equivalent. Next, a string hex_map is defined, which contains all possible hexadecimal digits, 0 to 9 for values 0 to 9 and AF for values 10 to 15. This will be used for mapping remainders to their respective hexadecimal characters. The conversion process begins by repeatedly dividing the number by 16 and prepending the corresponding hexadecimal digit to the result string. The remainder from the division, number %16, determines the digit to be used, and number // equals 16 reduces the number for the next iteration. This continues until the number becomes 0, ensuring that all hexadecimal digits have been generated. Finally, once all digits have been processed, the result string contains the hexadecimal representation of the input number, which is returned as the output. This approach ensures correctness for all valid inputs, including edge cases like the smallest 32-bit integer, -2 to the power of 31. This is the Java implementation of LeetCode problem number 405, convert a number to hexadecimal. The logic mirrors the given Python implementation. Key differences include handling type declarations in Java and using a string builder for efficient string construction. The solution handles signed 32-bit integers properly by converting negative numbers to their unsigned equivalent using long arithmetic. The hexadecimal conversion is achieved by repeatedly taking modulus 16 and mapping the remainder to the appropriate character using a lookup string. To solve this problem, the objective is to convert a given integer into its hexadecimal string representation. This includes handling both positive and negative integers within the range of 32-bit signed numbers. If the number is negative, we use its 2's complement representation. Let's start with an example where the input number is 26. First, we check if the number is 0. Since 26 is not 0, we move forward. Since the number is positive, no adjustments are needed. Next, we initialize a string hex_map containing all hexadecimal characters, from 0 to F, and an empty string result to store the final output. Now, we begin the conversion process. In the first iteration, we calculate the remainder of 26 divided by 16, which is 10. Using the hex_map, we find that the character corresponding to 10 is a. We prepend it to the result, making it a. Then, we update the number by performing integer division by 16, which gives 1. In the second iteration, we again calculate the remainder, this time 1 modulo 16, which is 1. From the hex_map, 1 maps to 1. Prepending 1 to the result gives 1 a. Finally, we divide 1 by 16, resulting in 0, which terminates the loop. Now that the loop has ended, our final result is 1a, which is the hexadecimal representation of 26. Let's move on to another example where the input number is -1. Again, we start by checking if the number is 0. Since it's not, we proceed. This time, the number is negative, so we adjust it using the 2's complement formula, number equals -1 plus 2 caret 32, which gives us 429, 496, 7295. With this adjusted positive number, we initialize the same hex_map and an empty string result. The conversion process begins. In the first iteration, 429, 496, 7295 modulo 16 equals 15, which maps to F in the hex_map. We prepend F to result, making it F. Dividing the number by 16 gives 268435455. In the second iteration, the remainder is again 15, which maps to F. Prepending F results in FF. We continue this process, repeatedly appending F until the number becomes 0. After multiple iterations, the loop ends, and the result is FFFFFFFF. This is the hexadecimal representation of -1. Finally, let's look at the simplest example where the input number is 0. In this case, we start by checking if the number is 0, and since it is, we immediately return 0 without performing any further processing. The output is simply 0, as no conversion is needed. This concludes the solution walkthrough for converting a number to its hexadecimal representation. Here, we analyze the time complexity of the solution step by step. First, the initial check to see if the number is 0 is a straightforward constant time operation, taking 1. Next, if the number is negative, we adjust it by adding 2 to the power of 32. This involves a single addition operation, which is also 1. Now, the main part of the solution lies in the hexadecimal conversion loop. In this loop, we repeatedly divide the number by 16 until it becomes 0. Each iteration performs 3 key operations, calculating the remainder using a modulo operation, which is 1, string concatenation, which is more complex as it depends on the current length of the result string, and integer division, which is 1. The string concatenation is the most involved part because, in the worst case, it could take k time where k is the length of the current string. However, since the string grows incrementally, the total cost across all iterations remains linear relative to the number of hexadecimal digits produced. Now, the number of iterations in the loop is proportional to the number of hexadecimal digits in the number. For a 32-bit integer, the maximum value is 2 to the power of 32 1, which results in only 8 hexadecimal digits. This means the loop runs at most 8 times. Additionally, since the result string is built in reverse order during the loop, there's no need for a separate reversal step, which avoids any extra complexity. When we combine all these factors, the dominant term in the time complexity comes from the loop, which runs k iterations. However, because k is constant and capped at 8 for 32-bit integers, the overall time complexity simplifies to 1. Let's now look at the space complexity. First, the hex_map string, which holds the hexadecimal characters, is a fixed-size structure with 16 elements, so it requires 1 space. Next, the result string is used to store the hexadecimal representation of the number. In the worst case, it can grow to 8 characters for a 32-bit integer, but since this size is fixed and constant, it also requires 1 space. Additionally, temporary variables like number and result are scalar values or strings with a constant maximum size, so their contribution to space usage is 1. When we add all these together, the overall space complexity of the solution is 1, as all space usage is bounded by constants. To better understand the efficiency of this solution, let's compare it with a naive approach. In a naive solution, you might repeatedly divide the number by 16, storing the remainders in an array or list, and then reverse the array to form the final result. This approach would require k space for the array, where k is the number of hexadecimal digits, and an additional k time to reverse the array. In contrast, the proposed solution avoids creating an extra data structure like an array by directly building the result string. This makes it more space efficient. Furthermore, since the maximum number of hexadecimal digits for a 32-bit integer is 8, both time and space usage are bounded by constants, even in the worst-case scenario, such as when the number is 2 to the power of 32 1. Finally, let's summarize the best, average, and worst-case analysis. In the best case, such as when the number is 0, the algorithm runs in 1 time and uses 1 space. For the average case, the time and space complexities remain 1, as the number of digits is constant, capped at 8 for 32-bit integers. Even in the worst case, when the number is the maximum possible value, 2 to the power of 32 1, the algorithm performs a fixed number of operations, making the time and space complexities 1. In conclusion, the solution is highly optimized for both time and space, with constant complexity in all scenarios due to the limited size of the input domain. When dealing with hexadecimal conversions, there are 3 common mistakes to watch out for. First, handling negative numbers incorrectly. In hexadecimal representation, negative numbers are not represented with a minus sign like in decimal. Instead, they use 2's complement for 32-bit integers. For instance, -1 is represented as FFFFFFFF. To handle this correctly, you need to apply a bit mask like number and 0xFFFFFFFF. Second, stopping too early when generating the hexadecimal string. Some solutions terminate as soon as the number becomes 0, but this can lead to issues with cases like number equals 0, which should return 0. A simple fix is to add an explicit condition for number equals 0 to ensure the output is handled properly. Lastly, inefficient string operations can slow down your solution. Repeatedly concatenating strings in a loop is costly in Python. Instead, store the hexadecimal characters in a list and join them at the end for better performance. Another frequent pitfall is misunderstanding how hexadecimal digits are mapped. Hexadecimal uses the digits 0 to 9 and the letters A to F for values 10 through 15, but some mistakes arise when these mappings are done incorrectly, such as assigning a to J instead of a to F. To avoid this, it's best to use a predefined mapping like 0 1 2 3 4 5 6 7 8 9 aptdef for clarity. Additionally, edge cases are often overlooked. For example, number equals integer.man_value, which is -2 to the power of 31 for 32-bit integers, can cause infinite loops or overflow errors if not handled carefully. Testing explicitly for such edge cases ensures your logic works for the entire valid range of inputs. Understanding the patterns behind problems like this can be crucial, especially in interview settings. Converting numbers between bases often involves techniques such as bit manipulation, like masking with 0xf to extract the last 4 bits, or modular arithmetic and division. Handling negative numbers with 2's complement is another key concept interviewers might test. Optimizing for clarity and efficiency is also important. For instance, using bitwise operations like shifting is often faster than frequent arithmetic operations. While built-in functions like Python's hex are convenient, they don't demonstrate your understanding of the problem's underlying logic, so interviews typically expect a manual implementation. Be prepared to articulate trade-offs and write test cases for inputs ranging from 0 to edge cases like -2 to the power of 31 and 2 to the power of 31. There are also several related problems that build on similar concepts, making them great for practice. For instance, LeetCode number 168, Excel sheet column title, involves converting numbers to a different base, specifically base 26. Its counterpart, LeetCode number 171, Excel sheet column number, reverses this process by converting back from base 26. Another related problem is LeetCode number 191, number of 1 bits, which focuses on bit manipulation, a skill that's directly relevant to hexadecimal conversion. Lastly, LeetCode number 190, reverse bits, is another excellent problem for deepening your understanding of binary representations and bit-level operations. Finally, let's explore some alternative approaches to solving this problem. One method is the bitwise approach, where you use operators like and to extract 4 bits at a time and convert them into hexadecimal digits. This is highly efficient since it avoids division, but it does require a solid grasp of bit manipulation. Another approach is division in modulo, where you repeatedly divide the number by 16 and use the remainder to determine the hexadecimal digit. This method is easier to implement but slightly less efficient due to the overhead of division operations. Lastly, you can use built-in functions like Python's hex or Java's integer.toHex string. These are fast and concise but may not be acceptable in an interview setting, as they don't demonstrate your understanding of the underlying logic. Each approach has its trade-offs, so choose the one that best fits the problem's constraints and expectations. Great job following along. To recap, we explored the problem, discussed its key concepts, and implemented a solution using bitwise operations. Remember, understanding hexadecimal and bit manipulation is valuable for both interviews and real-world applications. Keep practicing, and don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!